give you an economic example of this. Revenue, as you know, can be expressed as a function of price and output. So revenue is a function of P and Q. And in fact, the function is what? P times Q. P times Q, that's revenue. But suppose quantity demanded is some function of price. After all, the amount consumers buy will be a function of the price. And by the law of demand, we would have a dQdP is actually negative. So this is a perfect setup for the use of the total derivative. Now, we want the total derivative of revenue with respect to price. Suppose we want dR dt. Well, what will that be? Well, revenue is a function of price and quantity. So it'll be the direct effect of price on revenue, partial R, partial P, plus partial R, partial Q, times dQdP. This will be the total derivative of revenue with respect to price. Again, to help you remember this, an easy way to do it is to start off with the original function. Notice the total differential of R is just partial F, partial P dP, plus partial F, partial Q dP. That's the total differential. The ultimate source of disturbance here is price. So we want dR dP, so just divide both sides of this by dP. dP over dP is just 1, so that vanishes. That'll help you remember the formula. Now, in this context, I use F rather than R. But F is equal to R, so their notation is fine. Okay. So let me take this a step further. What is partial F? What is partial R, partial P?
Q.
Yes. Look at this right here. If you differentiate that with respect to P, then the coefficient of P is just Q. What is partial R, partial Q? P. And dQdP will just leave as it is, because we didn't specify what this demand function was, so just leave it like that. So the total derivative of revenue with respect to price is Q plus P times dQdP. Let me just play around with this a little bit, and we'll express this in terms of the price elasticity of demand. Notice I could put a Q down here as long as I put a Q up here. Okay. Because Q over Q is 1. So I can put 1 in the denominator as long as I stick 1 in the numerator. Then, what is this expression right here? What is dQdP times P over Q?
Elasticity, price elasticity.
Yeah, it's the price elasticity of demand. So I could rewrite this expression, dR dP, is Q, factor out the Q, times 1 plus the price elasticity of demand. So the RDP is equal to Q times 1 plus the price elasticity of demand. So we actually get an interesting result here. Suppose, now the price elasticity of demand is going to be negative. Now, suppose the price elasticity of demand, algebraic, remember it's negative? Suppose it's algebraically less than -1, meaning it's -2, -3, something like that. Then demand is said to be what? You recall? If the absolute value of the elasticity is greater than 1, demand is said to be elastic. Elastic. Yes. Yes. I can see Gene back there. The idea is it's very elastic. So if you graph it, it's very elastic demand. So in this case, what is the RDP? What is the sign of the RDP? Looking at this, yeah, Q is always positive, of course. What about this time, this expression in brackets? It's got to be negative, because this thing, whatever it is less than -1, so it's -2, -3. So this whole expression is negative. In that case, the sign of the RDP is negative, meaning price and revenue move in the opposite direction. So we actually have an interesting result here. When demand is price elastic, and demand is very sensitive to price changes, price and total revenue move in the opposite direction. So if price falls, revenue actually goes up. Because quantity demand is so responsive to price. But when you look at this revenue, notice revenue is P times Q. What's happening here? Price is falling by a little bit, but quantity is going up by a lot. So the total revenue actually rises when price falls. And also, if demand is elastic, suppose the price were to go up by a little bit, small percentage, then the quantity would fall by a lot. And so your total revenue would actually go down when price goes up. So this is a useful result. You may have learned this in your micro classes. When demand is elastic, price and total revenue move in the opposite direction. Okay. Who follows from this map right here? Suppose the absolute value, or suppose in algebraic value, the price elasticity demand is greater than -1. Greater than -1. I don't need parentheses here. Then demand is said to be inelastic. That would be like the example of cigarettes, where the price elasticity is -0.4. A -0.4 is bigger than -1. So we're talking about algebraic value here. So in this case, if demand is inelastic, go back to this expression. This elasticity is greater than -1, meaning it's, say, -0.9, -0.8, -0.7, something like this. And then the term in brackets is going to be positive. So in this case, the RDP is positive, meaning price and total revenue move in the same direction. If you raise price, total revenue goes up. If you lower price, total revenue goes down. And the intuition behind this is to look at this picture right here. Demand now is inelastic. So if you raise price by a certain percent, quantity will fall, but it will just fall by a smaller percentage. So your total revenue actually goes And finally, suppose the price elasticity demand is exactly -1. Then what is DRDP? Exactly -1. Then from this formula, what is DRDP? 0. Because if this is exactly -1, that cancels for 1, this is 0. Okay. And that means, in this case, total revenue does not change as price changes. Price goes up 1%, quantity falls by 1%, those two exactly offset each other. So total revenue stays the same. This is the idea of a total derivative. And the total derivative is useful in situations where you have a dependent variable, say in this case R, which is a function of P and Q. And these two variables are related to each other. So in this case, when price changes, output has to change by the law of demand. So we're really talking about a total derivative, DRDP, which is composed of two parts, a direct effect and an indirect. That's all for today. We will have the midterm Monday morning, 9:30, and it will be over the stuff we've covered up to this point. I'll only test you over stuff that we've gone over in class. So, it's the parts of chapters really 6, 7, and 8, and 9. that we'll go over. There's a couple of things that I still will talk about, we haven't talked about yet. For example, Taylor's theorem and the implicit function theorem. So those are two things I want to talk about. Taylor's theorem is from chapter 9, the implicit function theorems in chapter 8. So, but everything else you really are responsible for. James, do you want to say anything?
Just that reminder, if you haven't given me your yellow